Welcome everyone to day 2 of our Database Design Masterclass. I'm thrilled to have you back as we dive into some of the most crucial aspects of building robust and efficient databases. Today, our journey focuses on 3 core pillars: database normalization, entity relationship diagrams, and practical e-commerce database design. On the left, you see an illustration of database normalization. This is a structured process to organize your database tables. We start with raw, potentially messy data shown by those scattered document icons. Then we apply a series of rules known as normal forms, specifically 1NF, 2NF, and 3NF. Think of each as a filter, systematically refining your database to eliminate redundancy and improve data integrity. This makes your database more efficient and reliable. Moving to the right, we explore entity relationship diagrams, or ER diagrams. These are visual blueprints for your database. They help us map out how different pieces of information, or entities like customers, products, orders, and categories, relate to each other. We'll be specifically applying this to an e-commerce database design, learning how to structure a system that efficiently handles everything from product listings to customer purchases. By the end of today, you'll have a solid understanding of how to build well-structured, functional databases for real-world applications. Let's get started. This slide visually demonstrates the critical issues we face with unnormalized data, known as anomalies, and how database normalization provides elegant solutions. On the left, under unnormalized data, we see 3 common anomalies. First, the insertion anomaly. Imagine trying to add a new product to your inventory, but your database design requires it to be linked to an existing customer order. You can't add the product by itself, which is a major bottleneck and limits your data entry flexibility. Next, the update anomaly. If a customer's address is stored multiple times across different records or orders, updating it becomes a headache. You have to locate every instance and change it, risking inconsistencies if you miss one. This leads to inaccurate data and inefficient operations. Finally, the deletion anomaly. This is perhaps the most dangerous. If deleting a specific order record also unintentionally removes the only existing information about a customer who placed that order, you've lost valuable data. The customer record vanishes along with the transaction, which is completely unacceptable for business continuity. The large arrow in the center represents the normalization process. This is where we systematically organize the database tables and columns to minimize data redundancy and improve data integrity. Moving to the right, under normalized data, we see the solutions. The insertion anomaly is solved by creating separate tables for products and orders. Now you can add new products independently without needing an associated order, making your data entry much more flexible and efficient. The update anomaly is solved by storing customer addresses in a dedicated table referenced by a unique ID. When an address changes, you update it in just one place, and that change is immediately reflected everywhere it's referenced. This ensures consistency and simplifies maintenance. And finally, the deletion anomaly is solved. With normalization, deleting an order record only removes that specific transaction data. The associated customer information, stored in its own separate table, remains safe and preserved. You maintain complete customer history even after orders are processed or deleted. In essence, normalization is about structuring your database to prevent these frustrating and costly data integrity issues, leading to more robust, reliable, and efficient systems. Welcome back. On this slide, we're diving into the critical concepts of functional and transitive dependencies, which are fundamental to understanding database design and normalization. Let's start with functional dependency, represented as A determines B. Think of it as a rulebook. It means that for every unique value of attribute A, there is exactly one corresponding value for attribute B. For instance, your student ID uniquely determines your student name. This relationship is the bedrock of database integrity, ensuring data consistency and accuracy. If A functionally determines B, B cannot have multiple values for a single A. Now, let's move to transitive dependency, shown as A determines B and B determines C. This is where we often encounter redundancy. Here, a non-key attribute, like department ID, depends on another non-key attribute, such as department building, which then depends on our primary key, employee ID. While employee ID uniquely identifies department ID and department ID uniquely identifies department building, the direct link between employee ID and department building is indirect. This redundant path means we're storing information about the department building for every employee in that department. This creates redundancy and opens the door to update, insert, and delete anomalies. Our goal in database normalization is to identify and eliminate these transitive dependencies, thereby reaching higher normal forms, like third normal form, 3NF, and achieving a clean, efficient, and anomaly-free schema. This ensures our data is stored logically and maintains its integrity. Welcome to our session on database normalization, starting with the first normal form, or 1NF. This is a fundamental concept for sound database design. 1NF's core rule states, every column must contain only atomic, indivisible values. This means no repeating groups, no arrays, and no lists within a single cell. If a value can be broken down further into meaningful parts, it's not atomic. Observe the violation of 1NF example on the left. Our initial students table shows the courses column holding multiple values, like SQL, Python, database design for a single student. This non-atomic structure makes querying, updating, or even counting courses extremely inefficient and prone to errors. It's problematic for data management. Now, on the after 1NF side, we've restructured this. The students table now exclusively stores atomic student details, ID, and name. The course information is moved to a new enrollments table. Each course a student takes is now a distinct row linked by the student ID. So John's 3 courses become 3 separate entries. This ensures data integrity and dramatically enhances query performance and overall database maintainability. 1NF truly forms the cornerstone of effective database design. All right, let's dive into the second normal form, or 2NF. Its primary objective is to eliminate partial dependencies. What's a partial dependency? It's when a non-key attribute, one not part of the primary key, relies only on part of a composite primary key instead of the entire key. A composite primary key combines 2 or more attributes to uniquely identify a record. Consider our before example, the course enrollment table. Student ID and course ID form the composite primary key. The instructor name attribute here is problematic. An instructor is linked to a course ID, not a specific student's enrollment. Thus, instructor name depends only on course ID, which is just part of our composite key. This partial dependency violates 2NF and introduces data redundancy. To resolve this, we apply 2NF rules, splitting the data into 2 tables as shown in the after section. We now have enrollments with student ID and course ID as its composite primary key, and courses where course ID is the primary key for instructor name. Every non-key attribute now fully depends on its respective table's entire primary key, significantly enhancing data integrity and efficiency. All right, let's dive into the third normal form, or 3NF. Building on what we learned about 2NF, 3NF primarily focuses on eliminating what we call transitive dependencies. What exactly is a transitive dependency? Look at our initial employees table on the left. We have employee ID as our primary key. Employee name directly depends on employee ID, which is good. Department ID also directly depends on employee ID. However, notice department name. It doesn't directly depend on employee ID. Instead, department name depends on department ID. Since department ID itself is not the primary key, but rather another non-key attribute, we have a transitive dependency. Essentially, a non-key attribute, department name, is dependent on another non-key attribute, department ID, which in turn depends on the primary key, employee ID. This structure causes redundancy. For example, engineering is repeated for every employee in Department D10. If we ever needed to change the name of Department D10, we'd have to update multiple rows, increasing the chance of errors. To achieve 3NF, we perform a decomposition. As you see illustrated with the funnel, we split this table into two. We extract the department ID and department name into their own separate departments table, where department ID now becomes the primary key for that table. The original employees table then retains the department ID as a foreign key, linking back to the departments table. The result, on the right, is two tables that are 3NF compliant. Now, every non-key attribute in each table directly depends only on its respective primary key. This eliminates redundancy, improves data integrity, and makes our database much more efficient and robust. All right, let's explore the progression of normal forms. This slide illustrates the step-by-step journey our data takes, moving from raw, unnormalized input to a highly structured, efficient database in third normal form, or 3NF. This systematic approach is fundamental to good database design. We begin with unnormalized data, often characterized by repeating groups or multi-valued cells. Imagine a single field containing multiple phone numbers or a list of items. This structure makes querying and updating extremely complex. Step 1 brings us to the first normal form, 1NF. Here, our primary goal is to ensure atomicity, meaning each cell contains only a single, indivisible value. We eliminate those repeating groups, effectively flattening our data into a more traditional table format, and establish a primary key set, the unique identifier for each record. Next, in Step 2, we move to the second normal form, 2NF. The focus here is to eliminate partial dependencies. This occurs when a non-key attribute depends on only part of a composite primary key. To resolve this, we break the table apart, creating new tables where all non-key attributes are fully dependent on the entire primary key. Finally, Step 3 leads us to the third normal form, 3NF. This final stage involves purging transitive dependencies. A transitive dependency exists when a non-key attribute depends on another non-key attribute rather than directly on the primary key. We resolve this by isolating such dependent attributes into their own separate tables. The culmination of these steps is a database that is consistent, highly efficient, and easily maintainable. Each stage significantly reduces data redundancy and enhances overall data integrity, which are critical for any robust system. This slide illustrates the core components of an entity relationship, or ER, diagram, an essential visual blueprint for designing robust databases. An ER diagram provides a logical roadmap showing how information in a system is interconnected. Let's identify the key elements. First, entities are the real-world objects or concepts we store data about, like customer, order, and product, commonly shown as rectangles. Next, attributes are specific properties of an entity. For customer, attributes include customer ID, name, email, and address. Customer ID is underlined, signifying it as a primary key, a unique identifier for each customer. For the order entity, you'll also see customer ID, FK, a foreign key shown with a dashed line. This is crucial as it links an order back to its specific customer, establishing a relational connection between the two entities. Attributes appear as ovals. Finally, relationships define how entities interact. For example, a customer places an order, and an order contains a product. These interactions are represented by diamond shapes like places and contains. Together, an ER diagram uses these entities, attributes, and relationships to provide a clear, logical structure for our database. This blueprint is vital for planning, communicating design, and ensuring data integrity before any actual implementation begins.